Hi everyone, I hope you're all having a good day. And as the title suggests, I'm going to be talking about quantum tunneling today. In short, quantum tunneling is defined as the movement of an electron or other quantum mechanical particle through a barrier in which it is classically prohibited in doing so. Now, if that seems a little confusing at first, don't worry, it kind of is. But by the end of the video, hopefully it'll make a lot more sense. But before we get into the details, let's go over a brief summary of the historical background of quantum tunneling. In his 1901 article, The Sparking Distances Between Plates for Small Distances, Robert Francis Earhart discovered an unexpected conduction regime of gases between closely spaced electrodes. J.J. Thomson then commented that these findings warranted further investigation. Then, in 1926, Franz Rother measured steady-state field emission currents in a hard vacuum between closely spaced electrodes. Then, in 1928, Ronald Gurney and Edward Condon simultaneously solved the Schrödinger equation for a model nuclear potential and derived a relationship between the half-life of the particle and the energy of emission that depended directly on the mathematical probability of tunneling. Eventually, the study of semiconductors and the development of transistors and diodes led to the acceptance of electron tunneling in solids by 1957. So basically, quantum tunneling has everything to do with the probability of an electron crossing over a barrier in which it is classically prohibited from doing so. It is akin to saying there is a 15% chance at this temperature that I will be able to exit this room by moving directly through the wall. And it sounds crazy on a macroscopic classical scale, but things behave differently on the quantum scale. And this is because on the quantum scale, particles behave as both particles and waves. #wave-particle duality. If you look at the wave function of an electron, you will see something like this. And taking the square of the wave function gives you the probability density function of the electron. This means that you can determine the probability of the electron existing in some region of that space. But what's interesting is that if a barrier is placed in the way of the wave function, the wave does not simply abruptly end. No, instead what happens is that it tapers off through the barrier. It decays exponentially with the thickness of the barrier, but it does not disappear instantly. And this means that for a thin enough barrier, the probability function will not be zero on the other side, which means that there is a chance for an electron to go through, or tunnel, past the barrier and appear on the other side. The intensity of this tunneling can be measured by observing the tunneling current. So that's very cool and all, but what's even more cool is that it's not just an academic curiosity. Tunneling is used in several things, such as STM, scanning tunneling microscopy, tunnel field effect transistors, tunnel junctions, nuclear fusions in stars, and flash memory. I would love to dive into all these in great detail, but I'm only going to look at STM and nuclear fusion stars, because I like the diversity of scale between these two phenomena. An STM is an instrument used for imaging surfaces at the atomic level. It was developed at IBM Zurich in 1981 by Gerd Binnig and Heinrich Rohr, for which they won a Nobel Prize in Physics in 1986. STM works by placing a conducting tip very near to the surface to be examined, and a voltage difference, or bias, is applied between the tip and the surface, and this allows electrons to tunnel between them. This tunneling current is observable, and it's also a function of the distance between the tip and the surface, the bias applied, and the local density of states of the sample. The movement of the tip across the sample results in variations of the tunneling current, and this is sent to a signal processor, which is then displayed as an image for us to see. And from this technique, you can get really nice sub-nanometer resolutions of individual atoms on the surface. So that's how tunneling can be applied for an STM, which is something that we humans have created. But tunneling also happens in things that nature creates, like stars. The energy that comes from our sun comes from proton fusion reactions. But at the sun's core temperature of about 15 million Kelvin, there is not enough energy to overcome the Coulombic barrier associated with proton-proton interaction. To overcome this barrier, a temperature of about 10 to the 9th kelvins would be needed. But luckily for us, the atomic nuclei behave as particles and waves. So because of their wave-like nature, there's a chance for protons to undergo quantum tunneling as well. A simplified version of this would be saying that when the wave functions of two protons overlap, they're able to fuse together and begin the fusion reaction. Although the probability of this happening is very low, it happens every single second, and it allows the sun to shine as we see it every day. So that's quantum tunneling in a nutshell. It's a really cool aspect of quantum mechanics, and it creates a lot of cool things for us to see and to use, both in the lab and in nature. There's a lot of cool future tech that can be made from quantum tunneling, like single electron transistors, which I've talked about in my previous video, and I'm excited to see where this technology takes us next. Thank you all for watching, and have a great day.